reduced source type. So what is this reduced source type? That is basically the switched capacitor type inverters. So what is the switched capacitor type? That also we'll see. As I've said, most recent research that is in the field of switched capacitor based multi-level inverters. So that also I'll highlight here, so that you will get a clear picture of what is going on in the recent research. So that when you practically try to design an inverter or multi-level inverters for the photovoltaic application or for different other applications like drives application, statcom application, any other application, you will find out what should be done actually. Recently, what we should do, why this switched capacitor inverter is so much emerging. So you will get a clear picture of these things. And we'll see also how the new topologies can be designed. I'll also tell you here the new topologies that can be designed for this type of applications, what I have mentioned, how to develop a new topology, what should be your focus. So we'll see all the details on that. And in the second half, in the afternoon, I will tell you about the hands-on session on this type of development of multi-level inverter, as well as the photovoltaic integration, the MPPT control, and the most important part, that is the multi-level inverter control, that is the PWM control. So we'll see all these things in the hands-on session in the afternoon. So once you understand the theoretical aspects clearly, it will be no problem understanding the concepts, the basic concept and everything. I will try to highlight one by one in this presentation, and try to understand the theoretical concept in detail. If you have any doubt at any point of time, you can interrupt me, and we'll have a discussion on that. Whatever the doubts you are having, we'll discuss at the time. And if you once you understand the theoretical concept, I think you will have no problem understanding the hands-on session, what I will tell you. In practical, when you go directly to the laboratory and start developing a multi-level inverter for different application, for let's suppose a microgrid system or a photovoltaic system or a wind energy conversion system or different other applications, so you will face different problems. I will try to highlight here as many as problems what I have faced while developing this type of inverters. So that all these points I will try to discuss here, so that when you will go to the laboratory for development of this type of inverter, you will not find many problem. So before we start, as I have told, you must know that why we are focusing on microgrid. What is the reason behind development of this photovoltaic integration with multi-level inverter? So these things should be clear. So if you see this clean energy generation, clean power generation is most demanding for any electricity generation in this recent time. And among these clean energy sources, what we have, that is photovoltaic energy and wind energy, all these sources, what emerging sources are two types, that two different sources, that is solar photovoltaic and wind energy system, which are most leading type of sources, renewable energy sources, compared to the other types, right? As we all know. And this is done due to reduce your fossil fuel emission, the carbon dioxide emission, everything, the pollution should be reduced. So to looking into all this aspect, we are progressively developing the clean energy source based systems, right? So these clean energy source based system, when we talk about, let's suppose a photovoltaic system or a wind energy system, the heart of the systems is inverter, right? We all know at any point of time, we need an inverter to convert the power that is produced from the photovoltaic or wind energy system, and to feed power to the grid or some of the loads, if you have some local loads in standalone system, or if you have a grid connected system, you are trying to feed power to the grid. So in all these systems, we need an inverter, right? That inverter converts your DC input to an compatible AC output. So that can be fed to the grid. So here what this multi-level inverter is doing, because I told inverter, as we all know, inverter that may be a 2-level or 3-level inverter, but this multi-level inverters are emerging because it can improve the power quality, right? So when we develop a multi-level inverter, we will see the different types of inverter. multi-level inverters. So there you will see the harmonics in the output side, that is the AC side, is much lesser in a multi-level inverter. So that will enhance our system, like the efficiency also, and also the power quality. So in this, again, in the multi-level inverter, as I have said, when we design a multi-level inverter, the conventional type, will see that requires more number of switches, right? So more number of switches are required, as well as more number of input sources. So it's not just that we integrate a multi-level inverter to the photovoltaic system. It's not that only one photovoltaic panel will be connected. You will see there is a need of several photovoltaic panels. So how to reduce that number of input sources, as well as number of switches? So for that reason, again, switched capacitor type multi-level inverters are developed, which are very much emerging in the recent time. And again, when we develop a switched capacitor based multi-level inverter, you will see that when capacitor comes into picture, we all know that capacitor voltage needs to be balanced, and it needs to be regulated, right? So without any problem, how we can regulate the voltage across the capacitor? So that is our focus here. If we develop a switched capacitor based multi-level inverter, our focus should be how to regulate the capacitor voltage without any much complexity, because we are telling that we are designing switched capacitor based inverter for reducing the number of sources, for reducing the number of switches, for compacting the system. When we try to develop a compact system, our focus also should be on the control complexity, right? Our control complexity should be lesser. So for that reason, we'll see how the control complexity can be reduced without any additional closed loop controller, how we can regulate the capacitor voltages. So that type of system is called as self-balanced capacitor, where you will see a very interesting feature of this system, that we do not need any additional controller or sensors to balance the voltage across the capacitor. So that is the beauty of this switched capacitor type multi-level inverter. You will slowly understand why I am talking so much about this switched capacitor type. And I'll also show you in the recent time what are being developed in the recent 2 to 3, 4 years only. I'll show you what are being developed in the field of this multi-level inverters. Okay. So before we go in detail into multi-level inverters, so let us know the basics of this renewable energy systems. I think some of the speaker might have already talked about this, so I'll not waste much time on this. But I just want to highlight here, if you see the non-renewable sources are still there, but the most energy generation, if we see the solar and wind energy, that are slowly progressing. You see the yellow graph, that is from the last 10 years of graph. If you see, we have a steady growth on renewable energy share, right? So the power capacity of the renewable sources are increasing, and this is the last 2019 global report. And we see similarly, if we see the progress that needed for India to meet the target, because we have a target of 175 gigawatt, right? So that 175 gigawatt we are slowly progressing, and whatever target we have set on 2018-19, we have already achieved it. So we are slowly progressing towards our target to reach the 175 gigawatt during the 2021-22. So we'll slowly reach over there. And how we are reaching that is by developing so many large number of power plant, solar power plant and wind power generation sources. And to show you some of the examples, if you see here, we have a 648 megawatt of power plant in Tamil Nadu. And you can see the Kamuti solar power plant. So many large number of panels are spread over a wide area, and that is producing 640 megawatt of power plant. So you can believe 1 kilowatt of solar panel, if you want to install a 1 kilowatt panel at your rooftop, because people are now developing so many rooftop based your solar power plants, right? Or solar power, your park, you can say. So when you are developing this type of solar energy system on the rooftop for 1 kilowatt or 2 kilowatt for a general home application I'm talking about, where we need a 1 kilowatt or 2 kilowatt of power plant. So in that case, you can see that we are generally integrating 4 number of panels. right? That varies definitely. That varies according to the power of the PV panel. But generally, what is available in the market, I am talking about 300 watt of PV panel that is generally available. 300 to 350 watt of PV panels. That is monocrystalline and polycrystalline PV panels. What is available? So these panels generally, if we buy a 300 watt of PV panel, right? If we, let's suppose we connect five number of 300 watt of PV panels and in series parallel of course fashion. So that type of system can develop 1.5 kilowatt, right? So for 1.5 kilowatt of power, to get that much power, we are connecting here 4 to 5 number of PV panels. So you can think of, when you try to develop a 640 megawatt of power plant, how many number of panels you need, right? So that is the reason there is a large number of panels connected over a large area. And we have also the Reva solar power plant. We have 750 megawatt of power plant in Madhya Pradesh. And we can see the Bhadla solar power plant, that is the largest, one of the largest in India. That is, these are all Indian based power plants where the solar park you can see that is 2250 megawatt of power plant. So it is very large. And similarly, we have wind farms. Most the largest wind farms you can see here, that is in one of the, in Tamil Nadu, that is 1500 megawatt power plant. And we have a wind park of 1600 megawatt at Jaisalmer, right? So these are this to talk briefly about this wind energy system. If we see, there are this type of wind turbines. What you see, these are the horizontal axis wind turbines, right? So these horizontal axis wind turbines are most, I think, the widely employed ones compared to the vertical axis wind turbines because of the efficiency. In the vertical axis wind turbine, if you see the vertical axis wind turbine like Savonius type, and you have the Darius type. There are various types of wind turbines are there based on the configuration and construction. So if you see those Darius type, Savonius type, those type of wind turbines are generally employed for low power, not for the megawatt range of power, right? Or the Darius type is somewhat most means emerging type, but still the horizontal axis wind turbines of what that is using again 3 turbine blades. Why I am talking about 3 turbine blades? If you go detail into the renewable energy based systems, you will understand the horizontal axis wind turbines generally consisting of, initially what they have developed 1 blade type, 2 blade type, then they have checked with 3 blade. So most highest efficiency what they have achieved is the 3 blade type. So you can ask me why we are not then integrating 4 blade, 10 blades like that. So that all depends on the tip speed ratio. There is a factor called tip speed ratio. So if you calculate the tip speed ratio of a wind turbine, you will understand what is the optimum number of turbine blades should be, right? So based on the optimum number of turbine blade, we have generally fixed 3 number of turbine blades in each of the wind turbines. So these are the most widely used horizontal axis wind turbines, right? So this is also again onshore type, offshore type wind energy based systems are there. So this type of wind energy system generally employs different types of generators, and based on different types of generator also there are different types of wind turbines. So we'll also see that. So as I was telling you, in a photovoltaic system, if we see the basic block diagram of a photovoltaic system, I think all of us know what the photovoltaic the panels produces. So this photovoltaic panel produces DC output, right? So whatever DC output we have got out of this photovoltaic panel here, let's suppose this is about 100 volt. Whether this much energy what is produced from the photovoltaic panel will be sufficient to feed to this utility grid? No, we cannot supply this much that required amount of power to the utility grid. So in that case, what is our focus? What we are doing? Right, in this type of photovoltaic panel, what we are generally doing, we are integrating a boost converter, that is to match the required level of the utility grid, and we are, after that we are connecting an inverter, right? So as I told you already, inverter is the heart of the PV system, and that converts the DC input or the boosted output. We can say this is, as I've said, this is the boost converter, which is boosting based on the duty cycle, right? So based on the duty cycle and whatever the maximum power we are tracking from this photovoltaic panel, we'll see detail into that. What is the recent research also going on in the field of maximum power tracking systems, that also we'll see here. So based on the power output from the boost converter, that inverter again converts the DC to AC, and then to reduce some of the harmonics, we are fitting this LC type, L type, LCL type filters over here. And then transformers. Transformers are again step-up type transformers that are being used and that are connected to the utility grid. So this is about the overall block diagram of a photovoltaic system. So why I am showing this overall block diagram? Because you will understand the importance of power electronic over this, right? So what is the importance of power electronics? You can see that is the development of this power converters as well as the control of this power converter. Not only you will connect some of the switches to develop some power electronic converter, you need also a closed loop controller. You need also an efficient control to reduce the harmonics, first thing on the output side, to maintain the grid voltage, to maintain the grid current, okay, to reduce the harmonics of the grid current, to regulate the DC link voltage, right? So there are so many objectives in this type of system. So to meet all the objectives, you need to develop an efficient controller, right? So we'll see how the controllers are being developed, that also we'll see. And similarly on wind energy based systems, as I was telling you, there are different types of generators. Generally, we have doubly fed induction generator as well as your different wound rotor types generators, and there are varieties of the generators that are being used. Initially, we are trying to develop the DC motor, DC generator based systems, but which are, you all know, the DC generators are most costly, and you cannot rely on DC generators generally, right? So that is the reason people have moved to AC type, and we have developed this DA5G based generator schemes, where again this produces an AC output. Like unlike your photovoltaic system, which produces DC output, this produces an AC output, and that AC can be again, this again can be converted to AC to DC, that is a rectifier, and then you can employ, this is optional, right? You are employing a DC-DC converter or not, that is optional. But to this, for maximum power harvesting, this type of schemes are employed. And then after that, we are again connecting an inverter. As I've told, this is one of the important part of the renewable energy systems. We definitely need an inverter to convert the input, right? So why not we are directly feeding this AC output to the grid? There may be a question, but that is not the case, because you cannot feed it directly, because this will be not regulated. See, this wind energy system or the photovoltaic energy, the input sources that are highly intermittent in nature, right? The characteristics, if you see, that are highly nonlinear. So because of this intermittency and the nonlinear nature of this input sources or renewable energy sources, we need this power electronic interface to extract maximum power and to like deliver maximum power from these renewable sources to the utility grid or any of the loads, right? So as we have understand now, these are the basic components of a photovoltaic system, as I have already told you. So let us move detail into this photovoltaic system and also the importance of maximum power tracking, right? I am here. I don't want to again explain the block diagram, because you might have understood already what I was telling. You can see this right hand side of the picture where we are connecting a photovoltaic panel to the boost converter, right? So this boost converter, what is the purpose of this boost converter? That is boosting the voltage. That is boosting the voltage. Then we are connecting an inverter. So this inverter, initially what we have developed initially 2-level type and 3-level type inverters. What is the conventional or traditional type of inverter what we have already, that are 2-level or 3-level inverters, right? And then to obviously to improve the power quality, as I was telling, we are trying to develop the multi-level inverter based systems. So we'll discuss how we can integrate a multi-level inverter here. Then obviously we are connecting some filter, L type or LC type filter, then feeding the output to the grid. So here in this type of system, you need to understand your objective. What is your objective? Objective is to control the boost converter, because if you do not control the boost converter, your maximum power should be tracked first thing here from the input side, because I told you this is intermittent in nature, continuously changing the solar irradiation. So we need to extract maximum power, right, at every point of time. So that is the first objective. Second is controlling or regulating the DC link voltage. This is generally called as the DC link voltage, common DC link voltage. So we need to regulate the DC link voltage. That is, here I have marked it as VDC. So that needs to be regulated. That needs to be maintained almost constant. We to not to introduce much harmonics over the output, right? So this needs to be maintained constant. Then on the output side, if you see, we need to regulate the grid side voltage and current, also the harmonics. So when we are connecting and boost converter, okay, there is a switch, power electronic devices, we all know. These are generally MOSFET switches are used in boost converters. High frequency operation is generally preferred, right? So when we how to control this switch? So that switch can be controlled by the help of maximum power point tracking controller. So this maximum power point tracking control, what is its important, what it's doing, we'll see afterwards. So here try to look over the block diagram only. Okay, you will understand in detail about the controller and how it is working. Then after that, as I told you, you need a DC link voltage regulator. Here, this DC link voltage controller is connected to maintain the required DC link voltage. Let's suppose our required DC link voltage over here is 300 volt. We need to maintain the required DC link voltage. And generally, what we do, we generally employ PI controllers here. In this DC link voltage regulator, if you see, we generally employ PI controllers. What it is doing? It is tracking the set value. Let's suppose our set value is 300 volt, but there may be some fluctuation in practical, right? It may go to 280, 285, 290, 295, like that. So that fluctuation needs to be reduced. So that error will be processed through the PI controller, and it will try to maintain the required DC link voltage almost constant. Then our next objective, as I told you, grid side. On the load side or grid side, if you see here, power quality needs to be maintained. Under the sudden sag condition, let's suppose grid voltage is suddenly reduced to about 10%. That is called as grid voltage sag. Suddenly the grid voltage, let's suppose it is increased. That is called as grid voltage swell. So during the sag and swell condition, also, and all the other grid side disturbances, during sudden phase change or any type of disturbance, we need to maintain the power quality, right? So that is why most recent research also based on the maintaining of power quality. So to maintain that power quality, we need synchronization, right? That is done with the help of phase lock loop. We need a current controller here that will help us to produce the required PWM output. So all our requirement of maintaining the power quality on the grid side or the load side, that is based on the control of the inverter. So if the inverter is properly controlled, we can maintain the required output as well as required power quality, right? So this inverter control with the help of PWM control is not so complex when we see a 2-level or 3-level type inverter. But when we go to development of multi-level type inverter, we'll see the importance of this pulse width modulation control. So we'll see the different types of pulse width modulation control also. So whatever I was talking here about all the control aspects and the design aspects, we'll try to cover everything during this talk. And so this type of photovoltaic panels. So let us see the basics of this photovoltaic panel. When we buy a you might be wondering why I'm telling you about a photovoltaic panel. We would have seen thousands of times. No worries, you might have seen. But the thing is why I'm talking here, because to know about maximum power point tracking, you need to know in detail about a photovoltaic panel, right? When we buy a photovoltaic panel from the market, what are the informations available with you that you must know? Then only that will be helpful in developing an efficient maximum power point tracking control, right? So because here, when you buy a photovoltaic panel, this is the front view, this is the backside view. And on the backside, you see a terminal box. This terminal box, that is the zoomed version of the terminal box, is shown here. So this terminal box, as you can see, connects some of the diodes inside this, right? These are generally the the Schottky type diodes. Why we have connected this diodes, this bypass diodes, right? Have you ever thought of what is the reason behind this bypass diodes? And you can see there are two wires coming out of this. That is one of the red wire, black wire that indicates the positive and negative. So we are getting the DC output. And if you see on the back side of the PV panel, there is a rating, yeah, all the ratings of the PV panels that is mentioned over this backside, right? So what is mentioned over here? So here we'll get different informations. That is, what is the open circuit voltage of this PV panel? What is the short circuit current of this PV panel? And you will also get to know what is the maximum voltage of this PV panel. That can be what is the maximum voltage that this PV panel can produce. Similarly, what is the maximum current that this PV panel can produce? So these informations are provided to you. And also, what is the total power? This power output will be definitely, that is the multiplication of this BMP into IMP. That is the maximum voltage, maximum current. If you multiply, you will see the power output. So these are the data, and also the standard temperature, standard irradiation. Irradiation is nothing but the input solar energy that is falling on this surface of the photovoltaic panel, which is generally measured in terms of watt per meter square, as we all know, right? It may be 1000 watt per meter square standard. And because of the cloud, because of the presence of tree, and because of the presence of dust, this irradiation generally varies. So this solar panel, when we draw the equivalent circuit of the solar panel, which is generally a current source connected to an anti-parallel diode. Why we are taking a diode? Because what is the reason behind taking a diode here in the equivalent circuit? Have you tried to analyze? Okay, I'll leave it up to you everything, but I'm just telling you here, if you draw the equivalent circuit of this photovoltaic panel, you will see that it is generally represented with a current source, constant current source. So that is due to the solar energy falling over the surface of the photovoltaic panel. So you see, this is very simply the IPV, constant current source, as I have told, this is IPV, right? With respect to voltage, if I draw the curve. And if I get what is the equivalent current, what is coming out of this panel, if I try to draw that, and you can understand that is IPV minus the diode current. So this diode current with respect to voltage diode curve, you already know that is slowly, it will gradually try to increase. When there is a breakdown, it can increase, right? So based on this, if I try to calculate the equivalent current from the PV panel, that will be IPV minus ID. Very simple. So if you subtract at every point of time, you will get a curve like this. So this is the highly non-linear curve of a photovoltaic panel. And on this highly non-linear curve, there exists only one maximum power point over here. Because you see, at this y-axis, if you focus on this point, okay, this where the voltage is 0, but current is maximum, no doubt, but voltage is 0. So if voltage is 0, at this point of time, power will be 0. And at this point of time at x-axis, if you see, voltage is there, but current is 0. So again, power is 0. So power will start like this, and it will increase, and it will gradually decrease, and it will come to 0. So your power versus voltage curve will be like this. Okay, I'm redrawing it here. This will be your I versus V curve, current versus voltage, whereas this will be your power versus voltage, right? So this point where the maximum power lies, this is the power where maximum, right? So corresponding to this, the voltage and the current that are called as VMP and IMP. That is the voltage and currents corresponding to the maximum power point. Okay, here it is marked wrong. This is not VOC and ISC. These are the VOC. This is the open circuit voltage. This is the short circuit current. Whereas the voltage and current corresponding to the maximum power point are called as VMP and IMP. Okay, so just a second. Oh, it is not coming. Okay, so taken 3 different cells connected in series, 3 different cells connected in series, which are of very low voltage cells. You can say that is producing 0.5 volt, 0.5 volt, 0.5 volt, just for an example. So in series they are connected, so the output voltage will be 1.5 volt, right? in combination with the three cells, we can obtain 1.5 volt output. But for that cells, when they are connected in series, we can say the curve representing the overall three different cells will be something like this, right? Where you have a characteristics, very characteristics, you can see the IV characteristics of a photovoltaic panel. But these cells are not affected due to cloud, not affected due to tree. But suddenly, if one of the cells is shaded, that is called as shaded due to the presence of, as I have told, different obstacles. So one of the cells are shaded. Now what will happen? Now how the current will flow? Because you see the current direction, what is marked over here, that is in this direction. Current is flowing like this to the load, right? If you connect some of the load here, definitely current will flow to the load directly. But the problem is when the one of the cells is shaded, what will happen? This cell too will now behave like a semiconductive resistive material, and it will try to dissipate the energy output that is from the cell 1 and cell 3. Due to that reason, obviously the overall output from this photovoltaic combination will reduce now, right? You see the output from total output. Initially, the output was how it was produced, and now due to the shading effect, how the output is reduced, right? So this output is reduced. Why? Because this cell 2 is absorbing, or means the power output from the cell 1 and cell 3 is dissipated over cell 2. Now the thing is how to avoid this. So due to that reason, we are connecting this bypass diodes over each of the cells in a string. So if you are connecting this bypass diode, what is the function of this bypass diode? It will not be activated until and unless one of the cell is shaded. If suppose one cell is shaded at any point of time, then this cell will now bypass, and this current will flow through the diode in this way to the output, right? So now this diode will be forward biased. So this is the reason behind connecting this bypass diodes, and which are connected over this backside of the panel in a junction box. So this is how the IV or PV characteristics of a PV panel. This is some of the more detail of the this photovoltaic system or the characteristics. You can observe the I versus V curve and P versus V curve. You see here the current versus voltage curve. The current versus voltage curve represents uniform irradiation. But practical, it is not never uniform, because you will see the irradiation is like it is distributed, right? Internet connection is unstable. There may be some problem. Whether my voice is clear?
Yes, sir, it's fine.
Very
Okay,
clear.
thank you. Okay, thank you. So you can see here, if there are three PV modules connected like this in series, you can see the equivalent PV output. If the curve one represents this, if there is a uniform irradiation, right? Uniform irradiation means it is not shaded. But if one of this module, let's suppose PV module 3 is shaded, you can see the curve how it changes. So what is happening here? This power curve, corresponding power curve, if you see, this consists of a peak point, right? This is the maximum power point. But when it is shaded, you can see the equivalent curve is now consisting of multiple peak points. So that is the reason we are always in the interest of tracking this maximum power in any of the condition, whether it is uniform irradiation, whether it is shaded condition. In all these conditions, we need to track the maximum power point, right? Because when we track the maximum, because we can see the characteristics is highly nonlinear. That is the reason people are now trying to develop different optimization based technique, artificial intelligence based technique to track the maximum power point. Because if you have one maximum power point, one maxima, it is not a problem with conventional tracking system. When I mention conventional tracking system, that is your pot up and observe technique, the incremental conductance technique, right? So those techniques are generally suitable for the your tracking in case of one maximum power point. But when we see maximum power point, a number of maximum power points, or these are called as local maxima, global maxima. When all this concept comes, then in that time you need to employ some intelligent technique to track the maximum power point, right? So we'll see how this is being done. So just to understand the basic concept, let us first try to think a PV panel is connected to the load. Here I am trying to explain you what is the importance of this maximum power point tracking, right? Some of you might be knowing in detail, but still for some of you it is very interesting to know that why it is required. So here, if you see a photovoltaic panel directly connected to the load without any interface in between, what will happen? Let's suppose this is the load resistance, that is let's suppose R naught. I'm taking this as R naught. So what will happen in this type of system? So as we all know, this is the IB curve, the blue color curve, what is shown, and the red color one, that is the PV curve, right? The power versus voltage curve. So you can see that this point somewhere here, that is the maximum power point. Okay, but we as we have connected some load, so based upon the load, there will be a load line. So this load line, that is indicating, if you try to see the slope of this line, you will find out the slope of this line, that is del I by del V, that will be equals to your 1 by R naught, right? You all know this relation already. Del I by del B will be equal to 1 by R naught. So if I, let's suppose, try to increase the resistance, the load resistance in this type of system, if I try to increase the resistance here, load, if I try to increase the load, what will happen now? This load will gradually increase. So your curve will gradually shift to a new point. This load line will shift to a new point. So accordingly, as you go on increasing the load, you will see the load line is gradually shifting towards the right. And you will see when at this point of time, right, when your current is 0, voltage is there, but at this point of time your current is 0. So as current is 0, so if you see, the R naught will be equals to infinity, right? Infinite. So here, this R naught, where it is infinite, your system will behave like open circuit, and this is the called as open circuit voltage. Corresponding voltage of this point is called as, that is why open circuit. Similarly, gradually, if I reduce the resistor or the load value, if I reduce the load, you will see the load line shifts to a new point on this side to the left. So similarly, as it will match with the y-axis, at this point you will see your resistance is very minimum, or you can say that R naught equals to 0. That is because you can see that voltage is 0. Current is there, but voltage is 0. So R naught corresponding to this point will be 0. So as R naught is 0, this point is your circuit will behave like short circuit. So that is the reason this point is called as short circuit, or corresponding to this, the current is called as short circuit current. Corresponding to this, on the x-axis, the voltage is called as open circuit voltage. So we are drawing a curve here exactly like this, VOC and ISC. As I have told, we have one maximum point over here, so that needs to be tracked. But as you can see here clearly, as the load varies, because practically the load is not constant. You all know, right? Practically the load is never maintained constant. Load may vary at any point of time. So you can see in this type of system, if the load is varying, your load line is varying. So load line is varying means it may be sometime here. If it is sometime here, the maximum power point is now at this point. Corresponding maximum power point is now at this point. But this is not our maximum power of the PV panel. You can see the maximum power is somewhere here, right? If suddenly the load is increased, you can see the corresponding maximum power is somewhere here, right? But we are not able to track the maximum power, required power. We are not able to extract the required power. Why? Because the resistance seen from this PV panel side, let's suppose I am taking this as the terminal resistance RT, and this load resistance is R naught. Now RT and R naught, they both are equal, right? So when there is a change in load, accordingly your load line is changing, accordingly your maximum power point corresponding to that is changing. But our maximum power point that needs to be tracked is here. As I've told you, the manufacturer has already provided us the maximum power from the PV panel is, let's suppose, 1 kilowatt or 1000 watt. So we need to track the 1000 watts, right? But we are not able to track it because of the change of the load. So how it can be done? How it can be tracked? That only can be tracked. That is the reason we are isolating the load and the PV panel. This isolating is done by the help of the DC-DC converter. This DC-DC converter, generally buck or boost type converters are employed. What this DC-DC converter is doing here? So this DC-DC converter is now isolating this RT and R0, right? So now whatever may be the load variation, our input resistance seen from this PV panel side, that is RT, will be maintained always constant. That is our objective here. So how it can be maintained constant? That is by tracking the voltage and current from this point. So we are sensing the voltage and current. Control is generating the required duty cycle, because as I told you, boost or buck converter, that will consist of a one power electronic switch, right? So this power electronic controlled, so that can be controlled by the help of MPPT controller. So this will give the duty cycle to this DC-DC converter. So that is how this system is developed. And in this type of system, what we are doing, by sensing the voltage and current output from this point, we are getting first what should be the power, and we are slowly trying to track that global or maximum power, right? So that is how these systems are developed. This is the basic block diagram of a photovoltaic system. Neglecting all the load, when I say it can be, after this you can connect an inverter, grid or anything, or a battery can be connected, any type of system. So this is how our systems look like, where we are trying to isolate the load and the input resistance, as I've showed, the terminal resistance RT, right? So by that, let's suppose we have sensed the IPV, VPV. You all know this concept, the pot band observe or incremental conductance concept. So I'll just tell you what is the research going on. You might be wondering, P&O algorithm and incremental algorithm that are being developed long back, right? Long back, these techniques are developed. But why still I am talking about this? You will understand here. The major problem over this is you try to understand the major problem. So in this type of system, if you see, I have taken a simple logic over here. If the change in power and change in potential, change in voltage, let us consider this prior potential is voltage change and this is the power change. If both are positive, then the next potential side will be positive. Okay, because this, when I say P&O algorithm, this algorithm, I think you all might have seen a flow chart where we are sensing the VPV, IPV. Okay, in the afternoon I told you I'll show you the hands-on session on this also. So this VPV, IPV, when we sense it from the photovoltaic panel, then we are tracking, we are calculating the power. Then we are setting this old power, or this is, let's suppose, the power set power, you can say. And we are trying to see whether the new power after the change in the duty cycle, because this duty cycle will be continuously changing until and unless we track the maximum power. So when the duty cycle is changing, we will gradually see what is the change in power. If the change in power, that is, let's suppose that is the new power what is calculated, whether the change in or new power is more than the old power or less than the old power, that you need to see. This algorithm need to see, right? So if the change in power is and the change in voltage both are positive, that is the reason I have given this logic here to understand the flow chart. Instead of drawing a flow chart here, this logic will be much more easier for you to understand. If both are positive or both are negative, then only your movement will be towards the positive side. You will see what is this movement through this curve. We'll try to understand. And if your one of the voltage change or the change in power is negative, then I told you this will be your reverse direction or negative perturbation. So perturbation is what? Is perturb and observe algorithm is what it is doing. Let us now take a curve of this PV curve of a photovoltaic panel. Okay. So initially I am checking the movement. Let's suppose this movement is from here to here. As you can see, I marked it as 1. That is the movement number 1. Okay. So initially, let us consider due to the change in duty cycle, and the movement is from this point to this point, okay, or towards the one. As you can see, one is clearly shown here from this point to this point, okay. So what is happening at this point now? When it reaches a new point, it will see whether the change in power, change in voltage or prior perturbation, both are positive or not. So as you can see, I will clearly highlight here. At this new point, you can see this is the voltage, this is the power clearly. And old point is what? This is the old. So this is the voltage, this is the power. You see, now power has changed in positive. Clearly, voltage is increased, right? If you see the x-axis. If you see the y-axis, power has also increased. So both are positive. As I told you, if both are positive, you can take the next perturbation as positive. Okay. So now our algorithm will see that both are positive. So we must increase the power. So it will go to a new point 2. That is the reason it has moved to a new point 2. Again, at point 2, if you compare, you see there is a gradual increase in the voltage, gradual increase in the power. Both are positive. Again, the algorithm will now move towards the right or in the positive direction. When the algorithm is moving towards the right, at point, it will reach a point 3 on the right hand side of the MPP, because this is the maximum power point that you should not forget. But now we have tracked a point here, that is the new point at 3. What we have tracked is this. So at this point, if you see, and if you compare with the old point 2, you see voltage has increased in positive. But what about the power? What about the power? Power has decreased, right? At point 3, the power has decreased. Very simply, I told you if one of the thing is negative, then your next perturbation will be negative. So now the algorithm will see that our perturbation should change because one of the thing is negative. So it will again move towards the left hand side now. That is why you see the movement is 4. The fourth movement now at this point of time is towards the left hand side, not again towards the right. And then at 4 point, it will see again the same thing will happen. So it will try to move to this point. It will try to come to a new point. It will try to move to this point. So slowly what is happening here, you see, the movement is fluctuating. Means we are not tracking the maximum power. We are never able to track the maximum power. That is called as the oscillations near the maximum power point. We are not able to track the maximum power because there is a oscillation. Exact maximum power point we are not able to track, but there is a oscillation slowly from this left hand side to right hand side, then again to a new point. So that is how we are oscillating. So before we go on to this, let us understand here what is happening. You can see here what is happening in a perturb and observe algorithm. In a conventional P&O algorithm, what is happening? It is moving from 1 to 2, 2 to 3, then 3 to 2, then 2 to 1 again. So like this it is moving. So if I draw a voltage versus this time curve, you will find out the voltage change is like this, something like this, right? This MPPT voltage is changing like this. It is going to a new point on the left hand side of the curve, then right hand side, then to a new point. So we are getting a 3-level oscillation. But what we generally observe in the output side, it is generally like this. The voltage is like this. So this voltage, if you zoom out and if you see, you will understand that the voltage is changing in this fashion, right? That is called as the 3-level oscillation in the, or 3-level tracking mechanism. So this P&O algorithm or a conventional maximum power point tracking technique or the incremental conductance technique, these are all based on this your, what is that called, 3-level tracking. So what is the problem with this 3-level tracking? Why not people are doing research on this 3-level tracking type? Why not people might be using this P&O algorithm, incremental conductance algorithm, for different application, most widely employed type of algorithm, but still what is the problem? The 3-level oscillation, if you see the power loss, if you calculate the power loss, that is somewhat higher than the what is now currently we are doing. So what currently we are doing, I'll try to explain you that one. But before that, you try to understand the issue. Issue kya hai? What is the problem? You see in the incremental conductance algorithm, this incremental conductance algorithm comes from the pot and observe only, right? That is P&O algorithm. Actually, we see the dP by dB. Whether the change in power with respect to change in voltage is zero, more than your zero or less than zero, that is how to track. So this tracking process depends on the dP by dB, change in power with respect to change in voltage. That we always see. As I've told you through this flow chart or through this logic, we are checking? We are checking the change in power, change in voltage, right? So this change in power, change in voltage, if we try to break down, you see this dP by dB can be represented in this way, where power can be turned into I into V, and if you take a derivative, you can express this in this way, where this di by d term, that is the conductance. Okay, this del I by that is equivalent to del I by del B, that is nothing about the conductance. So this is dP by dB is directly or indirect proportional to this del I by del B, right? So we can write in this way. This thing can be written in this way, that is del I by del B equals to minus of I by B, because you try to understand this here. At maximum power, dP by dB will be equals to 0. So if it is 0, this del I by del B will be equal to minus of I by B. So obviously at maximum power point where dP by dB equals to 0, we can write del I by del B equals to minus of I by B. And on the left hand side, it will be less than del I by del B. And on the right hand side of the MPP, it will be more greater than the del I by del B. Here, within the incremental conductance, it's if you check the power losses and other things, it is more or less similar. Both the algorithms are more or less similar. But what is the issue? What is the issue with this algorithm? Issue is that if you see here, just try to understand here. It is very simple. You see, let us start again the movement on this curve. There are two curves here, two curves representing at different irradiation. Let's suppose this is at 1000 watt per meter square. And there is another curve at different irradiation level or of lesser power. Let's suppose this is of 600. Oh, sorry for this writing, because I'm writing with mouse. It may be difficult. So let's suppose this is 600 watt per meter square, corresponding curve. Okay, the second curve. Now try to see the tracking process. It is trying to initially move to a new point A. At point A, you can see at point A, your change in power is positive with respect to this new initial point. Change in voltage is also positive, right? Change in power is increased, change in voltage is increased. So based on our logic, if the prior perturbation is positive, change in power is positive, what we should do? Again, we should move in the positive direction. We have moved from point A to B. Sorry, not point A to B, we will move from towards the right hand side. But let's suppose at point A, suddenly the irradiation is changed. As I've told, at point A, irradiation is suddenly changed from 1000 watt to 600 watt. What will happen? If irradiation is suddenly changed, the new point on a new curve, because the curve will change to a new curve like this. So that is the reason the new point will now immediately shift towards this point, that is at B. Now at B, what is our algorithm will see? You see at point, you compare this point A and B. Our irradiation has decreased. Okay, that is the reason the point A is shifted to a new point B. What our algorithm will see? Which power is more, point A or point B? Obviously, point A is more. It means power has changed in a negative direction. But what about the voltage? If you see the voltage, no doubt the voltage is increased. But what about the power? Decreased. As per the concept, what I have told you, if one of the thing is negative, your direction movement should be negative. You see the issue now, you will understand is that when the change in power is negative, now at this new point B, our algorithm will see that my movement has to be negative. That is the reason it will try to reduce to this point. You see, that is the reason it is coming to a new point here that is marked as red color here. the movement is towards the negative side or towards the left hand side of the MPP. Our MPP is here on the new curve, our MPP is here. But whether we are able to track that MPP? No, we are moving in a wrong direction. That is called as drifting. If you focus on the recent paper, you will find out this term called drift. What is this drift? Drift is called as moving towards the wrong direction, wrong movement. But our MPP is on the right hand side, but our algorithm is trying to track to the left hand side. So after some of the movement, it will see again that, okay, no, I have to go to the right hand side, then it will come to right after one or two movement. But this has moved in the wrong direction, right? So this is the problem. And when there is a sudden fluctuation in the irradiation comes into picture, this type of algorithm, the conventional P&O incremental conductance algorithm, they can never track the accurate MPP. Okay, when there appears maximum power of different, let's suppose a curve is like this, the PV curve, due to a different irradiation pattern, you can see there are number of maximum peaks. Okay, so this type of algorithm will trap at the local peak, but what is our global maximum is this much, that has to be tracked. So these are the major issues with the conventional tracking technique, right? That is the reason we have moved to develop different new tracking techniques. Anyway, you try to understand the research topic here, what research is going on. Then, as I was telling you, in the conventional MPP tracking, you can see there is a 3-level oscillation, right? I was telling you about a 3-level oscillation. So how to avoid this? So if you see in the initial stage, I have told you already here, how we are tracking, how we are able to track the maximum power. We are sensing the voltage and current, VPP, IPP, right? Based on that, we are tracking the maximum power. But people are now trying to develop reduced sensor type MPPT techniques. Reduced sensor means instead of tracking IPV, VPV both, only sense VPV, and based on voltage, because this current sensor, when you are connecting a current sensor, that is Hall effect sensors are connected in practical. So when we connect a Hall effect sensor, what will happen? The noise will be somewhat more, oscillation will be somewhat more. But people have observed, if you see the literature, you will see only by the help of voltage sensor this MPPT can be tracked. So the one sensor can be reduced, right? So neglecting the current sensor, if you develop voltage sensor based MPPT technique, that is called a single sensor based MPPT technique. If you see what is the interesting feature of the single sensor based MPPT technique is that, you see, I am not tracking my maximum power point now based on the duty cycle variation or based on the change in voltage and current. I'm only looking for the change in voltage. And based on that, I'm calculating an objective function here. Okay, this objective function is not based on any algorithm. I have calculated. How I have calculated? You need to understand based on this your different type of converter. If you consider a boost converter, if you consider a buck converter, this objective function will be different. Okay, this objective function what I have mentioned here, that okay, this VPV term will not come. That is this will be the equation. So this is for the boost converter. So if you take into consideration a buck converter, this objective function will change. Okay, so that is calculated in this objective function. If you calculate, you can see that there is no term of IPV. Everything is converted into duty cycle and VPV. Okay, so if I draw a curve of this objective function with respect to duty cycle, that curve will look something like this, where you can see the movement tracking process is clearly shown here. Initially, the movement is from P to Q. Then it is moving from Q to a new point called R. At R, it will see that objective function is negative now. So based on the objective function, I will take a decision whether I have to move towards the right or towards the left. So at R, I see the objective function is now negative. You see the importance of this. When I see here objective function is negative, I will move to the other direction. So what is happening here? The movement is now in between R to Q, Q to R only. I started with P, okay? Corresponding to this P point here on the PV curve, my P is somewhere here on the right hand side. When it moves to the objective function, in objective function, if you see P to Q, I'm moving, here I'm moving P to Q, okay? Then Q to R, then R to Q, then Q to R, Q to R, then R to Q, it will happen, the oscillation. So what is happening? This oscillation, if you see, the movement is from Q to R to Q. So because of this employing the voltage sensor, I am able, yes sir, is there any problem?
No, sir, there is a disturbance actually. You can continue.
Okay. So you can see the output of this voltage sensor based MPPT single sensor. I am able to get the output of lower oscillation because the movement is from R to Q, Q to R. I am getting a two level output. You can see here Q to R, R to Q, R to Q, Q to R. So what is happening? In practical, if you see, the three level oscillation is much more, where in the two level oscillation is reduced, right? Oscillation is reduced, so I'm able to track most accurate power output. And when there is a sudden change in the irradiation, due to sudden change in irradiation, let's suppose your new curve is somewhere here now, when there is a sudden change in irradiation. So on the new curve also, when the movement is from X to, first movement is from W to X, here to here. Then at X, let's suppose suddenly the irradiation is decreased. When it is decreased, immediately the point will shift to Y, right? You try to understand. Immediately the point will shift to a new point Y. At Y, it will see that at Y, if you see the objective function, because I told you the decision will be taken based on the objective function. At Y, you can see the objective function is negative. If it is negative, I told you how the movement should be. The movement is now towards the other side. So that is the reason, instead of drifting, I mentioned you what is drifting. Drifting is moving towards the wrong direction, but we are here moving towards the right direction, right? So this algorithm or this type of technique never encounter the drift problem, and we will be tracking the accurate MPP where even if there is a change in the irradiation, okay, sudden change in the irradiation. So that is the advantage of this type of technique. So this is called the advancement or research. So people are trying to develop this type of technique of reduced sensor based. What in another point what I have not mentioned is that is the adaptive duty cycle tracking. The duty cycle needs to be adaptive. The value of duty cycle initially what we have to set here, that needs to be adaptive type, okay? Because if you take a fixed perturbation, the result may not be optimum or may not be good. So if you see, if you take a adaptive type perturbation, you will see the results are most interesting or more better, or the oscillations are more less. So that is how the research is going on. You try to develop reduced sensor type MPPT. You try to develop the MPPT techniques with different algorithms like your particle swarm optimization, genetic algorithm. These are already developed. Flower pollination based algorithm, and these techniques are already developed. This is one of our paper which you can follow for knowing in detail about this MPPT technique what I have mentioned here. Okay. So this is one of our setup in the laboratory. What we have a simple setup to test the MPPT always. You can see here, this is the 1 kilowatt of solar array soap panel. I think you all know about a solar simulator, or sometimes called a simulator. This solar simulator, as you can see, that comes with a software interface. Means without going every time to the rooftop, installing a real photovoltaic panel, how you will test the shading condition and all this, how you will shadow it, because you need again a covering sheet. You need a sheet practically, then you will cover it, you will check the shading condition. Means practically, if you want to test one algorithm, how you will test it? So to test it efficiently without going to the rooftop, installing a real PV panel, what you can do, you can buy a solar simulator, what comes with a this soft panel, where everything is mentioned. You can see the power, everything, current, voltage, and we are testing here. The MPPT controller is being programmed here, and we are testing. So we have a lab view environment to develop the MPPT technique. Different MPPT techniques you can develop and you can try to test it. I will show you some of the results here. you can see the measured power, or the calculated power from the photovoltaic panel when you connect to the load, when the solar simulator is not on, switched on. At that time, it is calculated 70.15 watt. And when your MPPT technique is enabled, MPPT control is working, at that time only this three parameter will show. So this parameter, as it's tracked, you can see we are able to track 70.1 watt of power. So almost accurate. So our efficiency of maximum power point tracking is almost more than 99%, right? So 99.5%. So we are able to track maximum power, more accurate power when the MPPT technique is on. But this is at 1000 watt per meter square irradiation. When the irradiation is changed to 500 watt per meter square, again you can see we are able to track 35 watt edge measured, exactly almost same. Similarly, at 300 watt, we are able to track 21 watt. So as we are changing the irradiation, we are able to track the maximum power, right? So this tracking curves and everything can be obtained from the solar simulator. So these are some of the results to make you understand in practical what you see, the voltage and everything. You can see the change in voltage. This I have already explained you just now. You can see the change in voltage is 3 level. Okay, 3 level change in voltage you can clearly see here. Whereas in the voltage sensor based MPPT, you can see a change of voltage in 2 level. It is moving in 2 point, sometimes called as 2 point type, and sometimes this is called as 3 point type. What is shown here in simulation also. These are the simulation result. This is the experimental result. You can see 3 point type tracking. 3 point type or 3 level type tracking is moving from your in the conventional tracking process, whereas this voltage sensor based tracking with duty cycle movement, that is called as the 2 level tracking. You need to know very much detail about it. There is a recent, some of the papers are there that you may follow for getting to know about this voltage sensor based MPPT. I have already mentioned you here most recent research. That is the reason it is going on. Still people are developing MPPT algorithm based on different types of algorithms. Jaya algorithm, ant colony optimization, and people have developed hybrid algorithm like combining this Jaya algorithm to P&O, ant colony optimization algorithm to P&O. So that is called as hybrid algorithm. So still there is a research scope you may try to explore on. Okay, you try to explore these techniques, try to develop the maximum power techniques. You can see in the last 2 years there are around several papers, 30, I think about 30 IEEE transactions are only there. I'm not talking about other journals. You'll see in IEEE transaction only about in MPPT, focusing on MPPT technique only in PV system. There are almost 30 IEEE transactions in last 2 years. So you can believe how the still recent research are going on in this field. Okay. So without wasting much time on this MPPT techniques, try to know something about your microgrid system. Now you have understood the basic concepts of photovoltaic panel, maximum power point tracking. So what we are doing in the microgrid system? In microgrid system, like we are trying to integrate more number of energy sources to the load, to the grid. So here if we integrate PV panel, battery, wind energy system like that. So in this type of system, what is necessary? The necessity is that only one major objective is that the power management and energy management. Because you are connecting multiple sources. Now people are developing electric vehicle application, maybe photovoltaic battery, supercapacitor based system, then your wind energy based systems. So all this multiple sources when you are connecting, one important focus should be on the power management. Okay. And one more important point I will tell you here, if you connect a battery, then you connect a supercapacitor. What is the reason behind connecting a supercapacitors? See, these batteries are having high energy density, but your supercapacitor like these are having high power density. It can immediately discharge, whether battery will slowly discharge, right? So this type of system generally connect a boost converter, PV panel, then battery supercapacitor needs to be charged and also discharged. That is why we are employing bidirectional converter. And we are feeding all the power to a common DC bus. common DC bus, then the power output from the DC bus is fed to the inverter. So inverter, I told you, that is the heart of the system where all the control parameter lies. Then you are feeding the power to the grid or to the load. So why I have shown you this type of block diagram with multiple sources? Because as I was telling you, our important major objective is to manage the power. Power management control, this is the important point. Okay. So this is the clear circuit diagram of PV battery supercapacitor based system. You can say how the power electronic plays an important role here. But this type of system generally operate in grid connected mode, and when the grid is disconnected, it will operate in islanded mode, or that is called a standalone mode. So this islanded mode of operation should satisfy one of the condition. What should be your condition? Your loads should get the power, your grid should get the power from the PV panel, from the battery, from the supercapacitor. Right? So what we need to do, as I've told you in the initially, if you remember, one of the major objective is DC-link voltage control. DC-link voltage control needs this DC-link voltage, the reference voltage, that we generally do with the help of PI controller, try to reduce the error. Then you need to sense the grid voltage, grid current. Why you are sensing this grid voltage, grid current frequency? That is to synchronize with the grid. The PLL technique, I have shown you the block diagram initially, if you remember. PLL will try to synchronize. So that needs the information of grid voltage, grid current frequency. Then this PV side, you need VMPP, IMPP, IPV, everything for MPPT tracking. Battery current you need, supercapacitor current you need, and the inverter current. These informations are required to develop a controller for the bidirectional converters of side, battery side, supercapacitor side, inverter control. Inverter control generally requires you need to take more decisions based on the grid connected or islanded system, right? Whether there is too much surplus power or lacking power. Surplus power means what? If PV power is more than the load demand, if the whether the PV power is lesser. So based on all these conditions, you need to develop the PWM control technique for the inverter. Then you need to control. So you see, when you develop a complex system like this connecting more number of sources, power management plays a major role. Okay. So you need to develop an efficient power management controller for this type of systems. Okay, and as I was telling you, electric vehicle, this is one of the important application, electric vehicle. So again, with this type of system where wind energy system, photovoltaic system, and other loads are connected, you can also think of connection with electric vehicles. Large number of electric vehicles are nowadays parked in the parking lot, right? When you park it, the batteries that is present in the electric vehicles that can act as a source when there are no power from the photovoltaic array or all these things. These batteries from the electric vehicles can discharge at a time to power a building also, and at the daytime when it is parked in an institute or in any organization, during that time you can charge your battery if you need it in the daytime, and also you can discharge whenever it is needed. So this is the Tesla and all this. There are many companies nowadays, they are developing different types of electric vehicles, e-rickshaw, e-auto, e-passenger car, all this type of system. So this is a major what is called important topic, what is research is going on in this field. Okay. So my focus is not here to develop a microgrid system, rather a multi-level inverter interfacing. Okay. So till now, whatever we have understood about the photovoltaic systems only, majorly, and basics of microgrid system. So let us see how this multi-level inverter plays a major role. Okay. There is some disturbance on the window. Let me. Okay. Okay, sorry for the disturbance. So here, as you can see, multi-level inverter that plays a major role, as I was telling you already. So what we are generally doing with the help of multi-level inverter, we are developing required staircase output. You see an inverter, a 2-level inverter or a 3-level inverter. If you see, a 3-level inverter comes from this basic concept that we can develop a 0 level, right? We can develop a 0 level. So in multi-level inverter also we have a 0 level, and we have some levels on the positive side. We have some levels on the negative side, and that is why this is called as multi-level output. Okay, which is not 3 level, more than 3 level. The 5 level, 7 level, it can be 9 level, it can be 11 level. These are all odd levels. So this is called as multi-level output. Okay, and this type of output, you can see that when you try to increase the number of levels like this, what will happen is that the output is nearing to the sinusoidal. That is the reason the output of a multi-level inverter contains lesser harmonics. Okay, if you try to check the harmonics or the total harmonic distortion, that is a factor used to decide the harmonics present in the voltage and currents. If you calculate the TSD, total harmonic distortion of the output voltage of a 3-level inverter, you see the harmonics will be much more than this multi-level type output, right? Here the harmonics will be reduced. So for that reason, what will happen when you integrate a multi-level inverter instead of a 3-level inverter, your filter size may be reduced, right? Because your harmonics are much lesser here. So the requirement of filter what you are connecting before the grid or before any load, that will be reduced. So that is the reason we develop a multi-level inverter based system. But what is again a problem? What is the issue? As I have told you, if you develop a multi-level inverter, if you see any of the circuit diagram of a multi-level inverter, the conventional type that are cascaded H-bridge type, or your that is based on the diode clamp type, or based on the flying capacitor type. You see this diode clamp flying capacitor no doubt requires a single DC source. This DC source can be replaced by the photovoltaic panel or by any of the renewable sources like this, right? So this picture, if you try to understand here, the cascaded HBridge type is most scalable and modular type, right? It is most fault tolerant type also. So when you integrate more number of HBridge, cascaded HBridge, number of HBridge, you can see that number of input sources will increase. So there is a requirement of multiple input sources, right? Also the number of switches will also increase. So our focus should be to reduce the number of switches. That is why we need to develop a reduced switch multi-level inverter. And we are also trying to reduce the number of photovoltaic panels. Because you see, if you integrate like this number of PV panels, no doubt you can get a multi-level output, but number of switches has increased, number of PV panels has increased. Requirement of DC-DC converter is optional, but still it requires. See, multiple DC-DC converter, if you connect, you need to control multiple DC-DC converter. So these are the problems over this type of systems. So our focus is to develop a multi-level inverter of reduced switch type. Okay, you can see some of the industrial used inverters. The Siemens, ASI, Rubicon, Alstom, Rockwell, all this is developed different NPC, neutral point clamp type, cascaded H-bridge type, flying capacitor type. So these three conventional multi-level inverters are most widely used in the industries as well as commercial systems, right? But why still the research is going on? That is to reduce the number of, or to compact the inverter, you can understand. So this is how the basic concept of a multi-level inverter is, where you can see if you integrate two H-bridge like this, okay, this is nothing but it is showing that number of H-bridges are integrated, but you think that let's suppose two H-bridges are only integrated, or let's suppose four H-bridges are connected. If four number of such bridge you connect, what will happen? You need four different sources, right? So four different sources, and these switches, what you are operating, the logic is very simple. Let's suppose the first H-bridge is switched at this point, some point alpha 1. Second H-bridge, we are switching at any another point, that is alpha 2. Third H-bridge, we are switching at alpha 3. Similarly, this is at alpha 4. So 4 H-bridges we are switching at different times. And when we have connected in a cascaded fashion and the common load to this point, what will happen? Due to that, the total output across this cascade edge bridge inverter will be like this. It will look something like this. 4 levels or 4 steps on the positive side, 4 steps on the negative side. You can see 1, 2, 3, 4, 4 steps on the positive and negative, and there is a 0 level. So this type of output is called as 9 level output. Understood? 4 level on the, or 4 steps on the positive, 4 steps on the negative side, and 1 step on 0 level. So that is why these are called as, this is called as 9 level output. So for commonly, if you want to calculate, you can calculate at any point of time. You can use the basic formula to calculate the number of level. Okay, the number of level can be calculated based on the number of DC sources. Number of DC sources, here you need 4 number of DC sources, I told. So this type of 4 number of DC sources, if you need, the number of level can be calculated accordingly. This is a 9 level inverter. So if you integrate 2 different, let's suppose now you are integrating 2 modules. 2 new modules means your output will be 5 level, where your output will be something like this. Okay, 5 level. Then there is a 0 level. Then in the negative side you have positive and negative. This is your 0 level. 2 steps on the positive, 2 steps on the negative, there is a 0 level. So this is how your output will be synthesized for a cascaded edge bridge type multi-level inverter. Okay, what I have shown you here. But the concept of reduction of number of switches, that comes from this. You see what is happening here. I have integrated, instead of DC source, I have directly integrated photovoltaic panels here. That is the beauty of multi-level inverter. You can integrate photovoltaic panels instead of the DC sources. Here you see, I have taken photovoltaic panels of equal rating, which is producing, let's suppose, the voltage VDC, VDC, and VDC. What is happening here? If you are trying to get the VDC output, VDC, you are integrating here the PV panels, and you are getting a 7 level output. That is shown here on the right hand side. You are getting an output like this. 3 steps VDC, then you combine these 2, then you combine all these 3 to get 3 VDC, right? So your output is 3 times the VDC or input source VDC, but that is by connecting 12 number of switches, because you have connected 3 H bridge. So total number of switches is 12. Total number of sources you need is 3. 3 PV panels you need. But you can reduce. How? You see the interesting feature here. What I've done, I have connected unequal rating PV panel. One is VDC, one is 2 VDC, or this is called as asymmetrical type of multi-level inverters. So if asymmetrical type of multi-level inverter you consider, if this is VDC and this is 2 VDC, you can still produce the required 7 level output. How? Now the first level can be produced by this first module, that is VDC. When the second module only will work, that will produce 2 VDC. And when both modules will combiningly work, then your output will be 3 VDC. So as simple as that, you are able to produce the required 7 level output using only 8 number of switches. One module is not required. No doubt your source rating has increased, but number of sources has decreased. You need only 2 sources, you need only 8 switches to produce the required output. So there is a scope of reduction of number of switches, right? You can reduce the number of switches. So that is why people have developed reduced switch type multi-level inverters. You can see the literature to understand the 7 level type inverter, multi-level inverters working. That is with the help of this cascaded edge bridge type. I am not discussing more on this. I will directly move to the reduced switch type multi-level inverters, which is the most interesting topic, most recent research topic, you can say. So I have divided accordingly. As I was telling you till now, we can divide into multi-source type and single source type inverters. Multi-source type, when we see, the advantage is that you can operate it with symmetrical, asymmetrical modes, but the disadvantage is that you need multiple sources, multiple PV panels, multiple converters, that needs to be also controlled. But when you see single source type, this is most advantageous type in my point of view, because you do not need multiple sources to control. Only one PV panel can be connected and you can get the required output. Now think, if you just connect one PV panel and one source, single source to get the required output, it will be much more useful, right? So we'll see the single source type that are the initially, as I was telling in the introduction, this is called, this can happen only with the help of switched capacitor based configuration. Okay, so what is this switched capacitor based configuration? We'll see. Just to highlight here, some of the symmetrical type and asymmetrical type reduced switch inverters I've shown here. These are not the focus here. So because the time is running out, so I'll try to directly go to the most emerging type of reduced switch inverters, what is developed. If you are interested on this, I can suggest you to go through one of our paper. This paper will tell you about all the different types of reduced switch multi-level inverters that are developed recently. Okay, all the types of inverter, also the application, also different types of component you can get to know about from this paper. Okay, so this is one of the inverter what we have developed initially. Okay, before we go to the switched capacitor type, what is that? Try to understand what is happening here. You see, initially we have developed a system like this by connecting number of PV panels. As I was telling you just now, if you connect number of PV panels, the problem comes with maintaining individual DC link voltage. Individual DC link voltage needs to be maintained. Otherwise, the required output here, let's suppose this is 15 level output, that cannot be produced. And 15 level output I am first getting with the help of only 10 switches. If you see the circuit diagram, only 10 number of switches I have connected. But if you compare a cascaded H-bridge type till now what I was explaining, okay, just to go back to the circuit diagram what I was explaining. Yes, here I was telling you here the basic concept. How many number of switches are required for if you calculate the number of switches here, you can develop a formula again how you can calculate the number of switches. How many number of switches are required for a 5 level type? 8 switches are required, right? So 8 switches are required means you can see that there are, because one H-bridge needs 4 switches. If you integrate 2 H-bridge, that will produce a 5 level output and you need 8 switch. If you integrate 3 H-bridge like this, you need 12 switch, where you can get the output of 7 level. So for a symmetrical, I am considering a symmetrical type. So for this type of systems, if you develop a 15 level inverter where you need 8 H bridges, right? If you connect, if you connect a 7 H bridge, then you can develop a 15 level output. 7 H bridge. So 7 H bridge means the number of switches will be 28. So instead of connecting a 28 number of switches, see how compact I have done. I have connected only 10 number of switches to produce the required 15 level output. So this is how reduced switch type inverters are developed. So here I have not focused more on that, how it is developed. We'll see the emerging type also. So you can see this is the one of the reduced switch type, but the problem here I will highlight is one of this problem is the number of PV panels. Okay, so when you connect number of PV panels like this, the problem is maintaining individual DC link voltage control, MPPT control, power quality control. So for that reason, we have developed a closed loop controller. In this closed loop control, we have developed the total voltage control, individual DC link voltage control, current controller, individual MPPT controller. So all these things are required. And you can see the experimental test setup we have initially developed. Why I am telling this we have developed initially, because this is not the reduced source type. No doubt the number of switches is reduced. Number of switches has come down to 10 instead of 28 if you compare a conventional cascaded H type. But whether the number of sources that is reduced, no, we still need multiple sources or multiple PV panels. So that multiple PV panel is the problem. So we'll see how interestingly we can reduce that one also. So you see, this is the initially we have developed one type of system. We have tested under different modulation index. You can see with modulation index change how the output of the multi-level inverter changing. At reduced modulation index, the output is not required 15 level. That is the important. But where the modulation index is nearly unity, our required 15 level output is produced. And also the grid current is maintained. Okay. So you can see the power quality analyzer we have connected to check the inverter voltage THD, grid current THD, where we have got the required THD of 3.9%, the voltage THD. Current THD is around 1.7%. So we are maintaining the IEEE 519 standard. I think you all know the IEEE standards that is required to be maintained, that is below 5%. So we are able to maintain here. But and okay, the some of the other results are shown here with change in irradiation. You can see when there is a sudden change in irradiation, our output voltage is not affected. That is the required objective. And when there is a sudden grid voltage sag is nothing but the 10% or some percentage drop in the grid voltage. The red color one is the grid voltage. When the grid voltage is suddenly drop, according to the grid current has considerably increased, okay, to balance the power. So the power is balanced here while maintaining the required 15 level output again. So this is the working of the reduced switch type of inverter, but still that is not the recent research I can say. No doubt there are major research papers are coming out in the field of reduced switch type, but I suggest you to look after this aspect what I will discuss now. That is the switched capacitor type multi-level inverter. So what is this switched capacitor based inverter? Try to understand. See, the traditional system that consists of a photovoltaic panel, a DC-DC converter, and an inverter, 2-level or 3-level inverter, like this, it is producing the output, where we need a DC-DC converter generally. And if you see a multi-level inverter, till now what we have discussed, the reduced switch type, switches has reduced, but whether the source count has reduced? No. We need number of input panels. But we are trying to achieve this type of multi-level output, what is shown on the right hand side. We are getting this type of output, but the problem is with the number of component and switches sources. Okay, so what is our objective here is to develop a switched capacitor type inverter that will connect only one PV panel or one input source and neglect the number of input sources, but still can achieve the same output as in the established or cascaded HVAC type or any other type of multi-level inverter. Okay, so you can see the interesting feature, how it can be done. So let us see the evolution. Here, if you understand this, the second half in the afternoon session, when I will explain you the hands-on, you will understand everything in detail. Okay, so you try to understand the concept what I was telling, what I am trying to tell you here, because this only I will try to tell you in the hands-on part. Okay, the switched capacitor type inverter will develop one of the inverter. You see, this is I have shown you a 3-level inverter, right? A single H bridge, if you consider how it is working. This T1, T2, when these two are operating, you can see the output is positive. When the T3, T4 are operating, output is negative. Very simply, we have got a 3-level output, and 0 level can be produced by switching on the upper 2 switches or the lower 2 switches, right? So we can achieve a 3-level output like this. Now you think of a multi-level output. I have already explained you 7-level. Just think about a 5-level one now. If you connect 2 different sources and 2 different H bridge. Now, if you are switching the H bridge T1, T2 first, okay, from the first module, this can produce a first level. Similarly, if you are switching on the second module, this can get you output of the sources can be combined. So you will get output of 2V. So if you take the voltage, let's suppose here 50 volt, here 50 volt, I am getting here 100 volt output. But why I am telling you this is not interesting? Because actually if you observe, you have got a multi-level output, staircase output. Harmonics may be reduced compared to this 3-level. 5-level has lesser harmonics, definitely. But the problem is what? You already have connected 100 volt in total. Yes or no? 50 volt, 50 volt, you have connected in total 100 volt. And you are getting 100 volt output. So this may not be interesting for you. So to make it interesting, let us develop a new inverter. The concept will be very same. So you see this circuit diagram now. on the right hand side. What we are doing here, I am connecting, instead of connecting two H bridge, like I have shown you I have explained you just now the cascaded H bridge type 5 level inverter. Instead of connecting two H bridge, let us now connect only one H bridge. And in the input side, I will integrate two input sources V1, V2 such that I will not connect a additional H bridge, but I will connect two different switches. You neglect this S3 switch. Now, for the time being, you neglect this S3 switch. Okay. If I connect two switches S1, S2 and one source, why? Because I know my objective. My objective is to add these two sources. Because at any point of time, if I add, then only I can produce the required 100 volt. Yes or no? By this connecting this H bridge in cascaded manner, what I am doing, I am trying to add these sources. So if you trying to add it, so let us add it in this way. You connect one switch S2, S1 in this way and one H bridge. Okay, what I am doing, you just see. Let us suppose I am switching on the switch number S1 first and T1, T2. If I am switching on S1 and T1, T2, how the current will flow? You can easily see current will flow through T1, T2 and it will come back through S1 back to the source V1. Only V1 is activated. Let's suppose this is again 50 volt. This is again 50 volt. My output is now very simply, I've got 50 volt output. One step because S1 is on. Now after some time, let's suppose at alpha 2, I am switching on switch S2. What will happen now? Because I am switching on switch S2, my current will now flow in this way from V2 switch S2 and it will add the voltage source V1 also in the same path in series, come back to T1, T2, back to the source. Very simply, I've got my output 50 volt plus 50 volt and here the second step I've got is 100 volt, right? So you see my output is now, and for the negative half cycle again, similar way I'll switch on these switches, whether I'll switch on T3 and T4 instead of T1, T2. So I'll get the negative half cycle. So my objective of getting an AC output of multi-level output of 100 volt has achieved. Yes, I have got the 100 volt output. This 50 voltage added. I've got the 100 volt output, right? But still the issue I will highlight here, the issue I will highlight here is that you see there are still needed of two sources, 50 volt, which I was again telling you in the conventional cascaded H bridge multi-level inverter. We still need two sources to add it. Then why, you can think of why I have connected this S3. I told you, right? I will tell you how to develop an inverter. So I'm trying to tell you here how you can develop yourself an inverter. You can now think, if this is not 50 volt, in one of the case, let us think that these two are not 50 volt. That is why I have written here V1, V2. Let us consider this is 50 volt, this is 100 volt. Now you try to develop the inverter and try to produce the steps. Okay, first when you switch on S1, your output will be, first step 50 volt I've got. Next step will be 100 volt. So if I switch on S2, now you think this 100 volt will be added to the 50 volt. Yes or no? Because current will flow in this way, both the sources will be added. So my output will be 150 volt, not 100 volt. So for that reason, I have connected a switch here S3, so that I can operate this inverter in asymmetrical manner also. Asymmetrical means when the sources are not equal, then also I can operate. See the interesting feature, I can get only S3 on, no other switches on. If I switch on S3, current will now flow through S3 only and my output will be only 100 volt. Then in the third step, if I switch on S2, my output will be 150 volt. So how many steps I've got in the positive half cycle? Instead of 2 steps, I've got now 3 steps. So obviously in the negative also I'll get 3 steps. So my output, instead of producing a 5 level output in like the last time, I am getting here a 7 level output. Yes or no? I'm getting a 7 level output. That is because only asymmetrical sources. But that is again not the focus. You can neglect these things now. Now the interesting part is you need to understand is that how to reduce the source then, because here I have taken two source. Again I have reduced the switches. Okay, neglecting the S3, how many switches are required here in this circuit? Only 6 switches. Here how many switches are required in the conventional circuit? 8 switches. So I have reduced 2 switches already. Switches are reduced, but whether the source number of DC source is 2. Here the number of DC source in conventional is also 2. So how to reduce it? So let us understand the concept and develop an inverter. Same way, same H bridge, in the same way why I have shown this circuit, in the similar way I am showing you another circuit here. What I have done here, I have replaced one of the source what is here, that with a capacitor, and I have connected a diode here because to obtain the output. How many switches here in the circuit? As you can see, only 2 here input side, 4 here as a H bridge. So I am connecting 6 switch. How many sources? Only one single input source, one capacitor. Okay. Now try to understand the operation. First, when I will switch on the switch, let's suppose I will switch on this a source. Okay, I am not switching on any other switch. Source, how the current will flow? You try to analyze. Current will flow through the diode because diode will be forward bias. Now at that point of time, let's suppose I am turning on T1 and T2, so my output will be positive. So I am getting my first step output 50 volt. Let's suppose this is 50 volt. Again, same 50 volt I am taking. At the same time, if I switch on S1 also during this first level only, if I am switching on S1 also, what will happen? Some current will also flow through the capacitor through the switch S1. Yes or no? Yes. Because of that, this capacitor will be charged to the input voltage of 50 volt. Very interestingly, the capacitor is now connected in parallel with the input voltage source, right? Because of that reason, the capacitor C is now charged to the input 50 volt, right? So what has happened? Because of that, then in the next step, if I switch on S2 now, I will turn off S1 I will turn off, S1 I will turn off, and I will turn on S2. Because the capacitor is charged to 50 volt, when I turn on S2 now, the diode D will be reverse bias, current will not flow through this. The input current will again now from the source, it will flow through the capacitor. In series, now the capacitor comes in series with the voltage source. Because of that, whatever the voltage stored in this capacitor, that is 50 volt, will now be added to the input voltage. So again, if I will turn on T1 and T2, my output is very simply now 50 volt source plus the capacitor voltage 50 volt. So the output is now 5 level. 100 volt I have got. See the interesting feature I will highlight you here. I have taken only one source of 50 volt, but I have got the output of 100 volt, twice the boosting. So as I have got twice voltage boosting, you think now whether this type of inverter, if I connect in a photovoltaic system, whether I need a boost converter. See, boost converter when I am connecting, that is to boost the voltage to 2 times generally by maintaining the duty cycle. Let's suppose around 0.5 I am maintaining, I can boost the voltage to 2 times. Here without any boost converter, from the input voltage V, I am getting 100 volt. That is by the help of this capacitor voltage. So I am boosting to 2 times without any boost converter. So we do not need an additional boost converter. First. Second interesting feature is that I told you initially, when you connect a capacitor, you need to think capacitor voltage, how to regulate. Whether I need an additional sensor, whether I need additional controller. No, you do not need anything here because you see, in parallel, initially it is charged in this way, current is flowing. In series, it is discharging. So we are trying to maintain in one half cycle itself, we are trying to maintain charging and discharging. Again, in the next half cycle, when the current is flowing continuously, again in the next cycle, this capacitor will be charged and discharged. So because of the charging and discharging in parallel and series, we are always maintaining the required 50 volt across this capacitor. without any voltage sensor or controller. That is the reason these capacitors are called as, or this type of circuits are called self-balanced switched capacitor type multi-level inverter. Self-balanced. See the picture. We are boosting to 2 times, and additionally we are not connecting any additional controller. It is self-balanced, and switches is reduced compared to the conventional type switches is reduced. Number of source is only one. So that is the reason I was showing you this type of circuit diagram initially. What we are trying to develop is this. We will get this required multi-level output connecting only one single source. That is by the help of this switched capacitor based inverter. Okay. Now I think you have understood the concept. In the second half, when I will explain you about this working concept of this in a MATLAB, then you will again understand much more. But be clear about the working. Working is very simpler. And this type of switched capacitor based inverter are developed very recently in 2014. And after that, only this concept of switched capacitor multi-level inverters are growing, emerging, and the people have developed many number of type of inverters. You can see here I have cascaded two modules. Just now, what module I have explained you, the same module I have cascaded two. If I cascade two modules, I have got 9 level output, because this module is producing 5 level, this module is producing 5 level. So 2 steps. If you analyze the steps, you will clear 2 steps here, okay, 2 steps here. So 4 steps I'm getting, that is 9 level output. But again, the problem, if I cascade in this way, the problem comes again, multiple sources comes into picture. So instead of cascading, or when you are extending to higher level, you should focus this type. These are some of the literatures you can see, which connects only single input source, as you can see. And it can produce any number of level, higher level, it can be produced with only single source. Clear? So my research during my PhD also, accordingly I've done it. I have developed a efficient high gain voltage boosting type, because till now people have developed very the boosting type. Why I'm calling it as high gain or voltage boosting type inverter? Because you can realize now we do not need a boost converter. We are able to boost the voltage, right? So that is why this I call it as boost type inverter, switched capacitor based, where capacitors are charged also automatically, self-balanced, without any closed loop controller. And also I'm trying to reduce the number of switches and sources. You see, I've connected only one input panel and one input single source. And from that, I've developed it in the laboratory, all the components. I will show you what are the components in a small video. And you can see I'm trying to get an output of 6 times the input. Means I have shown you all the operation, and the blue color paths are shown here to show the charging, discharging of the capacitor. I have connected in this circuit 3 capacitors. If you realize, C1, C2, C3, I have connected 3 different capacitors, where C1, C2 I am charging it to the same voltage as the input, whereas C3 I am charging it to 3 times the input voltage. Okay, so that is the reason I am trying to get the output of 6 VDC. If the input voltage is 10 volt, I will get here 60 volt. Do you still need a boost converter? Just think about it. Do you still need a boost converter to boost the voltage? No, because I'm anyway boosting the voltage to 6 times from one single input. So this working operation, for that you need to follow some of the papers I will show you at the end. This design aspect, the comparison has been carried out, how to get the required output, all this clearly analyzed here. See, this comparison, what I have done it with respect to different parameter like number of levels, sources, switches, driver, capacitor, the voltage boosting, and very important parameter I have not mentioned is the stress, voltage stress. Okay, in the afternoon, maybe if time permits, I will tell you a little bit about this, what is this, stress part and the cost factor. But now I will not discuss about much about it. I think the time is running for you, and time is given me up to 12 o'clock. So time is lesser, very less. So here just important point I will tell you. You can see here I have compared with more recent what is that called inverters. This comparison, if you follow my one of my paper, you will understand. I have compared only the inverters of very recently proposed ones, which are of similar types, switched capacitor type, that is developed in the last 2 to 3 years. You will see why I have developed this inverter. My proposed one, what we have proposed here, why this is very high gain type, why this is producing a 13 level output, and how we are trying to achieve high gain voltage boosting. So this has been tested in simulation. Okay, once we see the afternoon session, you will definitely realize how the simulations are done very easily. 30 volt is given as input. You see, I'm getting almost 180 volt here. I told you, right? 6 times the input voltage will get the voltage boosting. And the capacitor voltages, as I told you, two capacitors are maintained at the input voltage. One of the capacitor is 3 times the input voltage. That is also naturally maintained without any closed loop control. So these are tested under dynamic condition. Suddenly, when the input voltage is decreased from 30 volt to around 20 volt, you see the voltage, output voltage is also reduced accordingly without any disturbance. So these are some of the real-time results from the experimental test setup, what I've shown you with respect to nonlinear load, with respect to sudden load change. If you suddenly change the load from resistive to inductive, what will happen? See the pink color graph, this is the load current. The blue color one is the voltage, load voltage. Suddenly, if you change the loading, what will happen? The current will change accordingly, not the voltage. So that has been tested here. You see the pink color one, the resistive type load is changed to inductive type. When you change to inductive type load, your inverter should properly work with sinusoidal current, because inductor will act like a small filter. So your current will be sinusoidal. And if you connect a nonlinear load, what most of the people do not do the tests with nonlinear load, but if you connect a nonlinear load also, you can see the output is not disturbed. And these four results on the left side of one borderline what I've drawn, these are fundamental switching scheme results. And on the right hand side, if you see, the output is different. Yes or no? This is due to the PWM scheme. Okay, this is also 13 level output, this is also 13 level output. What is the difference? If you can observe, this is of lower frequency PWM output, this is of higher frequency PWM output. Clear? This frequency, higher frequency, lower frequency PWM concept I will explain you in the afternoon. You see some of the analysis done here with respect to efficiency and total harmonic distortion. TSD in the voltage is almost around 3% only. Efficiency is 95%, about 95%. And I have also calculated efficiency with respect to change in output power. So you can check this type of analysis you can do with new developed inverters. Okay, so let us see a small video of that. I have developed the inverter in the laboratory. Can anyone come, whether the audio is clear from the video?
So video is fine, but it's not audible. No sound is there.
No sound is there. So just a second. So this is my experimental setup, what we have developed in the laboratory. As we can. Okay, thank you. So this is my experimental setup, what we have developed in the laboratory. As we can see here, this setup contains some controller, the capacitors. These are mainly the switches which are controlled to get the. These are the inverter switches. Number of switches are used, and these capacitors are generally used for boosting the voltage. Instead of using multiple sources, we are using only single source, and we are boosting the voltage using these capacitors. And I want to show here the circuit topology what I have developed here. As you can all see here, there are generally 13 number of switches. I have named it as for convenient S1, S2, S3 like that, and up to S13. There are 13 switches are used here. and this is the load. Only one single DC source is used here. And for this DC source, I have used the programmable DC source from the laboratory. And these are all the 13 switches, with, as you can see, there are three capacitors, main capacitors are used, and this is the load arrangement. So for validation of this circuit diagram, what I have developed here in this circuit diagram, as you can see, we need a real-time controller. The DSP controller is used for that purpose. And these three capacitors out of this capacitor box, we have used three capacitors, as I have told. And there are 13 switches here. I have used only IGBT switches for generating the voltage output. And that is my load arrangement. As you can see here, the load arrangement is resistive and inductive load combination is connected. So from this setup, I have tested this output of this inverter. As expected, I am getting the more output voltage. Here, this is the voltage, the yellow one, and the green one shows the grid current, the load current across the loads. And these are the capacitor voltages. What we expect is, without using any control scheme, without using any additional control scheme, we can maintain these capacitor voltages. So all these capacitor voltages are maintained, balanced, and these are not distorted. So this is the output for one inductive load case. What I've shown, I'm getting here. The other outputs, I'll show it in this in the system what I've captured already. So here, as I've captured, as I've told you, this is one of the output. I'm getting the higher voltage output, the 13 level, you can say, output. And this pink one here is the current, load current. As you can see here, to test the inverter in dynamical environment, what I've done is I've changed the load here. So as you can see, this up to this point, the load is resistive, the pink one you can see. And here after this point, the load is getting inductive, so the current is nearly sinusoidal. That we are able to maintain. And for a different test case, I've used a nonlinear load, because generally in case of domestic applications, when you are supplying the PV power to home or anywhere, we may use some kind of nonlinear loads like iron or anything like that. So in that kind of applications, we need to be very careful whether our inverter is able to operate properly or able to maintain the voltage level without any distortion or not. Okay, so that's all about a short video of the real-time working model of this inverter, 13-level inverter of single input source, what we have developed in the laboratory. And most recently, I have also developed a new type of, again, 13-level inverter, but requiring some lesser number of switches. And again, single input source. This is also boosting type. So this is also validated in real time. And you can see the efficiency I'm achieving around 95%. The working concept I thought of explaining you in detail, but I'm sorry for that because time is running out. You can see how it is, but a little bit I'll try to discuss in the second half. And this has been tested, and this whatever I'm trying to tell you till now about the different maximum power point tracking concept, importance of it in the PV system, development of multi-level inverters, and not just multi-level inverter, not just the reduced switch type, also the reduced source type. Only single source or minimum number of sources how you can connect. That is by the help of switched capacitor inverter, switched capacitor concept when you integrate. I think you have understood the basic concept of switched capacitor, how it is balanced, the capacitor voltages in series parallel charging, discharging, how you are able to get the voltage boosting, and so many interesting features. So I think you will not leave any stone unturned to develop this type of inverter. I think you can definitely try to develop one on your own, so that whatever problems you are facing, whatever the things, issues there in the real-time development, we may see. And some of the other real-time aspects, how to develop in real time, how to do hands-on, not hands-on, how to start working on the MATLAB platform. So those things I will discuss in detail about this multi-level inverter, MPPT control, how you can start working on this. If you are interested on this topic, definitely you can understand in the second half. With this, I conclude this first session. And these are some of the papers I can suggest you to, if you are interested, you can follow. These are one of the, this year only, this year starting, we have published these two papers, which are all switched capacitor type. This is another paper, which is again switched capacitor type, self-balanced high gain multi-level inverter. And Also, I have worked, as I have told you, the major important part of this not to reduce the switches or compacting the size of the inverter, also to control the inverter, right? So control aspects, I will tell you when I will tell you about the MATLAB implementation. And when you develop a controller for this inverter, multi-level inverters, there is a very interesting concept of selective harmonic elimination. How we can selectively target the harmonic to eliminate from the output voltage, that you can see. So based on that, I have also proposed some of the control techniques, intelligent control techniques, or you can see some of the algorithms in these papers. So this is one paper about the controller. These are some of the papers. Also, there are some more papers are there. If you see on reduced switch devices, there are some other more papers. Switch the capacitor type inverter. So there are so many things are there to grasp, and I think you can, if you're interested, definitely you can work on it. And some of you might be knowing a very detailed any idea about these things. Some of you might not be knowing. Those who don't know, I will suggest them to go through it if interested to understand. And if I any problem, definitely you can contact me at any point of time in this email ID. So I think there might be many doubts, but in the second half, we'll discuss about this hands-on practice. Okay, I'm not going into this. So thank you for giving me a chance to discuss with you all these things, research aspects, and thank you for your patience hearing. Any doubts, I will be very happy to discuss, but based on the time, second half, I think we can get some more time to discuss in the second half. Let us see how it is going. Any any few important doubts? Any participants? I will check also this. No,
Participants, if you have any
there are
doubt, you
no
could ask.
questions in the chat box.
Hello, may I audible, sir?
Yes, yes, sir, please.
Sir, I want a doubt regarding the switching pulses. Okay, sir, you are
Yes,
designing some multi-level inverters, but how you are
yes.
giving the pulses to the switches, and
Thank
what
you
type
for
of
asking,
switch?
sir. As I've
Yes,
already told you in the afternoon session at 2 o'clock, which is starting, I'll be
yeah,
discussing in detail about the switching pulse generation, giving the output
right.
to a real-time controller, and how to develop a real-time platform of this multi-level inverter. I'll be discussing in detail about that.
Okay, sir.
Except
Another
that,
one
any
question.
other design aspect questions? Yes.
No. Did not the design expert question. I simply one question regarding the MPPT. Sir, you are discussing about the MPPT
Okay.
different technique, right? Like Pottabat observe method and incremental conductance method. Okay, and other types are
Yes,
possible,
yes.
like optimization technique are also possible to optimize or compute the maximum voltage and current, right? But it is practically
Yes.
feasible that we are using some optimization technique to compute the maximum power point. It is practically visible any possible real-time condition. Yeah,
Means if I get your question correctly, you are trying to ask about whether it is possible to develop a artificial intelligence based controller for the MPPT or not. Am
right.
I right? Is that the
Yeah.
question?
Yes, sir.
Yes,
Definitely.
because this whatever I'm talking about, talking here, that is based on the literature survey, what is available, what is done, what we have
Yeah.
done in the laboratory. One of the paper,
Yeah.
I think it is in my, if you can go to my Google Scholar, I think you will find out those papers on MPPT or some tracking technique also, some one or two papers are there. You will see this artificial intelligence based technique, whatever I mentioned, the Jaya algorithm, your ant colony optimization,
Yeah.
and your different other algorithms like gray wolf optimization.
Sir.
There are like several algorithms. Like in 2019 and 20, if you see only, I think there are around 40. some different algorithms are published in IEEE transactions. If you try to follow some of the papers, you will understand it is really possible, and people have already developed these controllers, tested in real time in very fast dynamic environment.
Sir, actually,
Yes.
the problem is that when we are designing or implementing that type of MPPT algorithm, then we have required more time, because the optimization technique is operated according to your RAM system.
Yes, definitely. Your controller size and everything matters, but people have also tested the tracking time. The tracking time is in fraction of seconds. If you try to follow those papers, you will understand that is why I was trying to tell you about the research topic, the oscillation, 2-level, 3-level, these concepts what I was trying to give you, that are all the recent research topics. And they in those papers, if you follow, I can suggest some of the papers if you want to. There are many papers are there on MPPT. You see those papers. They have, in every paper they have calculated the tracking time, tracking efficiency. If the tracking time is fraction of second, and if you are able to achieve the tracking efficiency of more than 99%, the MPPT tracking, then there is no harm. You can definitely go for that.
Okay, sir. Okay, sir.
Yes.
Okay. Thank you. Thank you, sir.
Yeah. Thank you. May I know your name, please, sir?
Buddhadev, sir.
Or you are a research scholar?
Right. Yes, sir.
So there is another question in the chat box. If you can find.
I think in the chat box there is no questions till now. I can see.
The question is.
In the chat box there is no question.
The question is, if you have more switches, how to provide the pulses to all the switches?
Yes, I think that question has been asked already. Because that exactly the same part I will discuss in the second half, so I am not answering now right now.
Okay. Any other queries, dear participants? Okay, sir. Let's end this session here. Thank you very much, sir, for this nice explanation regarding the photovoltaic, the MPPTs, its tracking technologies, microgrid systems. We have discussed the electric vehicle as well, and the multi-level inverters. That is a reduced switch type and reduced source type was really incredible kind of thing. And we'll love to see and do it on hands-on training session in the next step. And dear, thank you very much, sir. Dear participants, the next session will be started at 2 p.m. Yes, thank you. Dear participants, the next session will be started at 2 p.m. It will be a hands-on training session, and whatever sir has discussed, we'll have some hands-on training over MATLAB. So if you have your MATLAB installed in your system, kindly do present with that and kindly try to practice live along with Kaibole sir. Thank you all. See you at 2 p.m.